Welcome everybody to the next video. So we're gonna work on application development with SDRs. So this is going to be a lot more interactive than dealing with files. So an API is an application programming interface, and if we use an API with our SDR, we don't have to save files and then open them. We can work with the SDRs directly. So there's different APIs. SDRs will typically come with an API from the vendor, but we're going to use the SoapySDR API. It's this here. So it's a C++ library, and you can see there's different functions here, and we use these functions to interact with the SDR. So C++ is good when you need performance, but if you're just developing algorithms or testing ideas, Python is more than sufficient. So we're going to use this Python binding for it, and I took the script already and I changed it up a bit. So if you don't have Soapy, you can just install it with Anaconda. It's probably the easiest way. And if you prefer to do it from the source, you can also go to their GitHub and do a git clone. So anyhow, the first thing to do is to import SoapySDR. So we can do that as such. So this first app, the most basic thing I can think of is just making an app to view signals. So the first step is to just make sure that Soapy can see the SDR. So you can ignore this error here, but just warning. So it sees my SDR that I have connected. So all you have to do is make a SDR object, and you give it the driver of the SDR you're using. So if you're using USRP, just change this to UHD. If you're using HackRF, change this to HackRF, etc. So I'm gonna run this here. So basically what you do is, once you have your SDR object, you can give it a sample rate. I'm using 1 megahertz. Give it a center frequency. I'm using 900 megahertz. Give it a gain value. I'm using 20. And then you do that with this set API. And you can also use a get API. So you can see here I'm taking my gain variable, I'm taking my gain value, and I'm saving it into a variable called my gain. And the next important thing to do is to make a streaming object, RxStream. So just tell it if you want to use a receiving or transmit. I'm only using receive now. And then the data type, complex float 32. You can check out the last video for more explanations on this IQ data types, but anyhow, you'll just make a buffer, because this buffer is going to take the IQ samples. So after that, you just have to activate your stream and then make this function call to read stream. So it's going to read from the stream that we just set up. It's going to put the IQ samples in a buffer that we put here, and this tells us how many IQ samples to read. First one always gives -1. We can just do it again. Okay, so this output here, it tells you how many IQ samples it read, and then you get a timestamp as well for supporting SDRs. So anyhow, we have our IQ samples in Python right now. We didn't have to open any files. So what we can do is, I'm just gonna look at the first 1024 IQ samples, and I'm gonna plot them. Something that I didn't do last time is I'm gonna take the magnitude, absolute value of the IQ samples, then I'm gonna square that to get the power, and we're gonna plot that as well. Okay, so here's our IQ samples, the blue and the orange, as we expect. It's a sine wave, complex sine wave that I'm receiving. I'm just using an SMA cable and putting it directly into the SDR. What we notice now is that this green line, it's the absolute value, which is around 0.5. So this represents some uncalibrated voltage level that the ADC is sampling. So what we do, we don't want to work with voltages, we want to work with power. So you just square this voltage to get the power. So you can check that 0.5 squared is a 0.25, what I'm printing out right here. And typically we work with decibels, so that's really easy to do. You just take 10 times the log 10 of that power value, and then we can print that out. So you can see that we're getting around -6 dB full scale. And just as a reminder, a value of 1 will give us 0 dBFS, because 1 is your maximum power level that we can read, or that we can register with our ADC. Anything above 1 is going to get clipped. So you can just imagine that if this red line was at 1, if you go down half the power, 3 dB, that will put us at 0.5. Then we go down another half power from 0.5 to 0.25, and that would be another 3 dB, so -6 dB. So we're slightly above we're slightly above 6 dB, but just wanted to help you understand where this -6 comes from. So it's from converting this linear power level, 6 dB down, into a decibel scale. Okay, so now let's plot this. I'm going to use this PSD function like last time. So you give it the IQ samples and you tell it the number of frequency bins to use. I'm going to use 1024. So this function, it plots the decibel scale, but the power values that it gives you is in the linear scale. So what I'm going to do here is I'm just going to convert it to dB real quick, and I'm going to print out the index that has the maximum power, and I'm going to print out that power level. So here's exactly what we expect. So this is a sine wave into frequency domain, just a single tone. And we can see that the power is again around -6 dB. So this is going to be a little weaker because this is just the power of this one frequency bin. So it's ignoring the power that's in this noise. So it's a small amount of power in the noise, but it's still some power. So this is perfectly fine, what we're seeing here. So now this next part is optional, but I just want to make note that, this -6 dB right here, it's just a digital value. So basically I can make a sine wave here. It's totally simulated and make it have an amplitude and a power of 1, and it's going to tell me 0 dBFS. So it doesn't correspond to anything in the real world. To make it correspond to something in the real world, we have to calibrate this output. So the first step to do would be to just take note that we applied some gain. So we used 20 dB of gain. That means that any signal that we put into the SDR, it's actually, at the input of the SDR, it was 20 dB weaker. So what we're going to do is just subtract our gain that we applied. So you're not actually reducing any gain or making it weaker. All you're doing is you're just shifting everything down to account for the fact that you applied some gain inside the SDR. So now here's our new signal. It's exactly the same, but instead of -6, our peak is at -26. So you could say that this is the power level at the antenna port before you applied your gains. So the reason to do this is because you can't really say that a signal is weak or strong without any context. So for example, you could have a very weak signal, but if you put 100 dB of gain inside the SDR, you can saturate your SDR and overload it. So, but you can't really say that the signal itself is strong, so it depends on how much gain you put. So this is optional, but if you're into measuring signal strengths or depending on your application, you might have to do this. But then a note is that even this -26 here, it's not calibrated. So, it's not a spectrum analyzer calibrated in the factory. So what you would want to do though is just calibrate it yourself. And for me, I know that I used a -50 dBm signal. So all I have to do is I'm going to just make a variable called reference signal, -50, and I'm going to subtract that with the peak that I registered here. And then I'm just going to add this calibration offset back to the curve. So now this orange line, the peak here is around -50, which is exactly correct because I'm just injecting it directly into the SDR, ignoring cable loss. And you can see that now our y-axis is in dBm. So this curve corresponds to a real-world power level, and you can see the noise floor is around -120 dBm. So again, that's optional, but let's do something funner, which is to make this function ourselves. So there's different reasons you would want to make it yourself, maybe optimizations. For me, I made it because it gives you back some power values in a way that I didn't want. So basically, if you want to just adjust it, it's easy just to make it yourself. So here it's just a few lines. I'm gonna comment this out for now, just to show something to you. So to calculate the power spectrum in the frequency domain, the first step is to use the FFT. And whenever you use the FFT, just divide by the FFT length. Just remember that to scale it properly. Then we're going to shift the FFT to make it centered around 0. And then the next step, just like in the time domain, we can take the absolute value and then square to go from voltages to powers. And then we'll convert it to decibel by taking a 10 log. So now I'm going to plot that, the homemade function, with the built-in matplotlib PSD. So you can see it looks different. So this blue is the one that we just made, and the orange is the built-in function. So they're both correct. You can see the homemade one is a little weaker. That's because you have more power here now in the side lobes. And the reason they look different is because the matplotlib uses a window. So we can also use a window. So just I'm going to erase this 2 for now to show you one more thing about windows. So now we used a window. The shape is exactly the same, but you can see our function is shifted down a bit, and even the max power, instead of -6, it's -12. So the reason for that is because Windows actually reduces your power. It attenuates the signal digitally. So this is the window that we're applying, and then this is our actual signal. So you can see the green line, which is the windowed signal multiplied by the window. So here, where the window goes to 0, when we multiply that with our signal, the signal strength drops a lot. And same with the other side. So to account for the window attenuating your signal, every window has a constant that you have to multiply the IQ signal by. For a handing window, it's 2. So now if I just put that adjustment back in, you can see they look exactly the same. In fact, you can't even see it because they're on top of each other. So this power level is -6.3, just like the first time. Okay, so something else about this signal here. If you're wondering why it's showing from 0 to 1024, those are our frequency bins. So we're using 1024 frequency bins. So if you want to turn that into frequency on the x-axis, you take the sampling rate. For us, it's 1 megahertz. That shows how much spectrum we're looking at. And you want to calculate the frequency resolution. So since we're using 1000 bins, 1024, you divide your sampling rate by the number of bins that you're going to output. And so that's approximately 1000. So here, 976 hertz to be exact. So now, when you look at the x-axis, it's exactly the same as before, but instead of 0 to 1024, it's going to be 1 megahertz wide. And then we can add your center frequency here, like what I'm doing, and that just shifts everything up. So we don't have to do that. It would look the same, but now it's going to be centered around 0. Okay, so another thing to talk about is these large dips here. So there's nothing wrong with that. This is just normal behavior, but if you're wondering, it's just because of we're not using any averaging. So we took 1024 IQ samples and we used 1024 bins, so there was no way to average anything. But if we're gonna just go ahead and take our whole buffer, 8192, if we use it into this built-in function, it's gonna average anything above the 1024, so it'll take 8 averages. And now we have the exact same peak level but now the noise floor looks more flat. So we can do the same thing with our homemade function, except what you should do is take your buffer of 8,000 IQ samples and turn it into a matrix. So it's gonna give it 8 columns or 8 rows, and then the other row / column is gonna be 1024. And then the same thing with a window. Instead of a 1D array, it's gonna become a 2D array. I'm just gonna stack it on top of each other 8 times. And then we can multiply our IQ matrix with our window matrix. And after that, everything else is the same. Okay, sorry. Just run this again. Okay, so you can see that it's exactly the same. So it's now that I showed how you can write different functions in Python to interact with your IQ samples directly. I'm not gonna go over this line for line, but basically all of these functions that we wrote, we can just use a second script. So I'm gonna just open this up to show you what it's like. So okay, so it didn't open the RTL. That's because it's stuck with this process. So let me just kill that. So now we should be able to open it. Okay, so here's our sine wave. We're looking at it live, and we can do things like pause, zoom in, start it again. So the reason we can do this is because we're using an API and we have everything in Python directly. So I'm not going to go over the code, how to do everything, because now it's not an SDR topic. It's just how to use Python to make GUIs and to plot things. But I'll make this code available, and I hope you enjoyed making our first SDR application. Okay, thanks a lot, guys.